che avvio la registrazione, ma non... Ecco, ok. All right. Looks like we are in business. Good afternoon, everyone. Let me share my screen here. Do you have any questions so far before I start?
Professor, actually, we wanted to ask some questions about the homework, so I don't know if it's better to do it now or later.
Sure, we can do it now. Yeah.
Okay, because some of us have already tried to do the first part, and from a comparison, it came out a very strange thing that if we do the first block alone, we get a plot for the one with the kinetic part, so just the solving the Euler's equation. We find a plot for omega that is not the right one. Then we add the second block, and we adding the kinetics, and I don't know, there's some kind of back reaction, and the plot for omega becomes the one you showed us yesterday. And the same adding but the Euler angles, at least for me, are not the right ones. I don't know.
I would.
For me too.
Yeah, it may be.
Me too. Yes.
Okay, it may be that the numerical integrator that you're using is different, and so when you start adding different equations, since it's a variable step, it's selected automatically by simulink. By having it working with different types of differential equations, is adjusting steps and doing something different when you start adding more. And so I have, what did I have? Let me open here. I think I had variable step ODE 45. Is that what you have?
Yes.
That's the standard one.
Well, I'm not sure that it sets it that way. Variable step. The default one was actually auto, which I don't know what it's using. Basically, you're telling simulink use whatever numerical integrator you want. Okay, so I'm opening mine. Eventually. Yeah, we can definitely spend as much time as we want on this assignment and the next one, because I budgeted 8 hours, which is probably too much of class time on these. So if there are issues, definitely we should discuss them together. Okay, modeling, all the settings. My computer is not cooperating much today. Okay, so this is what I have. Oh, haha. I did have a manually entered maximum step size. Forgot about that one. Do you have automatic there? Because I think it comes default with probably with auto.
No, personally, I changed it.
To what?
OD 45.
Yeah, but the maximum step size, what do you have here?
Sorry. Let me check.
Yeah, I mean, it's
I think you also set a very low relative tolerance.
Tolerance as well, yeah, could be. Yeah, I'm sorry that I developed these some time ago, and I probably should have mentioned these settings, which I'm not suggesting in any way that this is the solution, but let's try to say, if I go to auto, what do you have here as the default tolerance, Maybe auto as well, right? I think it comes with that.
minus 3.
Oh, wow, that's very different, yeah. You said -3, right?
Yeah.
Okay. So I'm sure that this is going to look very different now. Yes, it's completely, actually, yeah, these are different. Remember the second angle, where the second angle was actually, they were on top of each other. This was growing all the time. Yeah, it is absolutely different. I think it's just the grading accuracy. The angular velocity is still the same, I think. But now I go back to what I had, and you may remember that they were different, right? So how do you know when you reach the best configuration? Well, it's difficult to say, but I usually do not ever have the maximum step size free to do whatever it wants. And here I had a much higher tolerance. I think this was coming from actually the next homework, which has a lot more going on. And I believe that I had to play with the settings for that one to get a meaningful result. And I guess they were just these ones. So I moved them to this homework. Yeah, so now I'm back to, plots like these. These are the other angles coming from integration. The second angle from the comparison, they are on top of each other. Yeah. So that may be what you have. Have you tried? Were you able to try while I was talking, maybe? Miss Barjaki, right, was telling me about this issue? No?
Yes, it was Maria Grazia, but we all have the same problem.
Oh.
So
Okay, sorry. She's gone now. Has anyone tried? Like now?
Yes, I have, and I still have a problem for the Euler angles coming from the quaternion, but maybe maybe it's a problem in the program. I need to check it.
So let's look at these, and I mean, you're more than welcome to share your screen, but this is what I have. Maybe you can double check.
Yes, I didn't write the DCM. I directly wrote the Euler angles in terms of the components of the quaternion. But obviously, with the redefinition of C13 in case it's larger than 0 in absolute value. But I think it's the same, so maybe just problem of maybe.
So when you say you didn't write DCM, you just wrote the elements that are needed, not every element. Is that what you mean? You're still doing an arc sine and arc tangent, right?
Yes, for example, for the theta angle, I just wrote the arc sine of minus arg, where arg was defined to be directly
that element
times to 1. Yes, just didn't write the, but I think it should be totally the same. So maybe it's just a mistake in writing the.
And for the other two angles, you make sure they use 8 arctangent 2, because that way it's able to go to the different quadrants. But okay. Anything else we should look at, or you want to try these first? You want to try to see if you have an error? I mean, you can share your screen and show me if you like.
Yes, but okay, maybe I will check later if all the formula are correct.
All right.
Okay, probably just one thing that I found out. I tried to simulate by changing the tolerance. Instead of putting 10 to minus 3, I put the one that you got in your code, 10 to minus 12, and it seems it is better on the omega and the Euler angles.
Yeah.
So I don't know if
yeah, you need to tune it to your problem. And sometimes when you start having high angular velocities, and 5 RPM is not that high. I mean, it's a reasonable angular velocity. When you start having things moving faster, it's best to be stricter with the numerical integration. I think if I mean, this may work, but if you go with attitude equations, I've always had trouble with fixed step integrators, for example. So if I just go with these, I don't even constrain the maximum time step. I don't know what it does. It may work, but my guess is, yeah, see, it's not even, it crashed. So the first attempt, it says that it cannot do it. There is a singularity, so basically the solver is not good enough. Then maybe if I go and constrain the fixed step to be that same one that I had before, automatic solver, I don't know, maybe a classical Runge-Kutta would work. It may actually work. Let's see what it does. But then my guess is when you start adding more complex issues such as the variable speed Kilimanjaros and everything else, it may not be that great. So this seems to be working, actually. I think the plots are pretty much the same. Yeah. So up to you. I mean, I'm not gonna tell you which solvers you need to use, but the goal of this exercise is, I mean, I'll share this with you once you're done. They should pretty much look the same, and especially the other angles that you extract from the quaternions and the ones that you are numerically integrating directly from the kinematics equations, they should definitely look the same, especially in the range, the initial range, minus pi. But this is good, absolutely. Solve the homework and come back with questions. Because if git control, does someone want to present something? No. What I was gonna say, yeah, because these issues that you face now may be applicable to the next more complicated assignment, and so it's better to sort them out now. Any other concerns?
Professor, just a question that is actually very trivial, but it's because I never used simulink before. How do you plot together two different functions? Because I
like two lines on the same plot.
Yes.
Okay, so basically you call the plot the first time. So you plot the first line, and then the command hold on will keep that image open. So I'll show you how it's done here. Callbacks. Okay, so the way I'm doing it here, for example, let's see, this is just one line. Okay, like here, I open a figure, I plot the first time quaternion 1, then I issue the command hold on, and then plot again. And from that point on, you can add as many lines as you want. Instead, if you don't put this hold on, the next plot command may actually open a separate figure. I think that's what it does.
Okay, thank you very much.
Yeah, no problem. Any other MATLAB Simulink questions? Okay.
Oh, yes, one question.
Yes.
For example, I don't have the normalization block.
Oh.
Is it normal?
Pun intended, right?
Me too.
Really, you don't? Let me see. Well, you can definitely put a function there that does the same operation, obviously. I mean, it's just take the vector and divide it by its norm. So take q
Yes,
and
yes.
we do q. That's weird. What version of MATLAB do you have?
For me, 2020B.
Normalize vector. Yeah, I don't know where I got these actually, the way this thing looks like. But I find this block that is called normalize. For example, what is this thing?
I guess it's from a specific toolbox.
Maybe. Yeah, which toolbox is this?
I think it's DSP system toolbox.
3D animation, this thing is. Oh, the block that I am using?
It's the same for me, and is on the left part of your window.
Yeah, you're right. Yeah. Yep, so that could be the case, that you don't have the toolbox. You probably don't also have the aerospace block set, do you?
I don't think so.
Yeah, because even us at the University of Florida, they give us MATLAB licenses, but the default toolboxes do not include the MATLAB aerospace toolbox and its simulink. The aerospace block set is not included. So, for example, see there is a normalized quaternion block actually in the aerospace block set, which I'm sure doesn't do anything special. But so I would say that you just grab a function and go in it and just do it manually.
Yes, it is what I've done.
Yeah.
It was just to ask.
Yeah. Good question. The same reason why I shared with you that the DCM2quat mine function, because since you don't have the aerospace toolbox, that may be useful in general for the future. And so some of these things, if they're MATLAB files, you can kind of copy and save them with another name. Okay. Well, let me know if you have other thoughts about Simulink. We'll start. We have 3 hours. Well, minus 20 minutes. So I'll definitely take a break at some point every hour or so. But if you recall, the final goal of this class is that big Simulink block. And I think I want to press on. And after this astrodynamic refresher, maybe we'll start deriving the equations of the spacecraft with momentum exchange devices inside, so that we can attack that problem, that homework 2, as soon as possible. So hopefully you're done by Wednesday. You don't have to, but I would like to be with you as much as possible for that assignment, because it's a lot of equations inside different blocks. So, but anyways, if you recall that model, there is a block to the left-hand side, I think it was, that it's simulating the orbit of a satellite. Because, as you can imagine, once you are in orbit, you can define different desired directions. For example, if you have to take pictures at the ground, you definitely use the position vector of your spacecraft as one reference along which you need to point your camera. So you definitely want to know where you are in space in terms of the center of mass to issue attitude commands, because not all locations require the same orientation usually, okay? So a refresher on astrodynamics is something that I think I want to do, even though probably for most of you there's nothing really surprising or new. So if you go back to this diagram, if you think about it, what we've done is rigid body mechanics. We kind of covered already kinematics and dynamics very intensely, but that's basically what you're doing with the homework 1. I briefly mentioned the disturbance torques. We haven't described torque-free motion. If we have time, we'll next week probably or so. if we have time, we can cover a little bit of these topics that are not necessarily in the syllabus, but I think they are important. Torque-free motion is, for example, stability of the spin. If you don't have any other torques outside and you put your spacecraft into spin about one axis, when is it stable or not? And it's down here actually in the passive means, but I consider that as part of torque-free motion as well sometimes. So maybe we'll see disturbance torques more in details, and definitely we're dealing with active eventually stabilization, which is three axes stabilized with, in particular, reaction wheels and CMGs. That's our focus, and variable speed control moving gyros, just to make it more general. But as we said before, we definitely need knowledge of our position in space, because the perturbations are a function of that, of your altitude, of your location above the planet, and so they're absolutely important. So we want to cover some of these today. And also particle mechanics. If you recall what we've done yesterday, you had a few slides on Newton's laws and the kinematics for a point, the acceleration, the relative acceleration, Coriolis acceleration, and all those are basically particle mechanics. But now we specialize it for orbits, okay? Well, everything is based on the laws of Kepler, as you know. The orbit of every planet is an elliptical path that can collapse to a circle around the sun, and the sun is occupying one of the focal points of the ellipse. The line that connects the sun and the planet will cover the same areas in the same times, so the surface speed, if you want to call it that way, is constant. And then the square of the orbital period on the trajectory that is closed of a planet is directly proportional to the cube of the same major axis of its orbit. An ellipse has same major axis, same minor axis. Now Kepler enunciated these laws for planets, but we know they are true also for artificial satellites around planets, like everything that we put in orbit around the Earth, which is what we care about. In particular, the first and simplest model for the force that is acting on a satellite or an object is the gravitational attraction force, of course. If you have two masses, they attract each other with this expression. R is the vector that connects the two. You can define it as going from mass 1 to mass 2. Action, reaction, the third law of Newton tells you that if M1 is attracting M2 with this force, then you have an equal and opposite force acting on M1. And the model for F12, so the force acting on particle 1 due to the attraction from 2, is a force that points positive with R because of the way it's defined, and it's given by the product of the two masses divided the cube norm of the distance in the direction of R, as we said. So it's actually divided by the square, if you like, because there is an R and an R cube down here. And then G is the universal constant of gravitation. And this is true for planets as well. So this law is valid not only for point masses, but it's also valid for objects that are basically spherical, a uniform mass distribution. So M1 doesn't have to be a point mass. It could actually be a planet that is spherical, and the mass is density is constant basically throughout the sphere. How do you prove that? It's quite simple. You would basically apply a similar force for the infinitesimal masses around the planet. So maybe trying to play with my overhead camera since now it's working. But I will stop sharing the screen to do so, because otherwise you don't see anything. Now I'm bigger, right, on your screen, I hope. Should be bigger. Can you confirm that the video is much bigger and it's focusing on the sheets?
Yes.
Okay, good. Because
Yes.
can't share and do this at the same time and have a reasonable size. So if your mass M1 becomes bigger, but the mass is uniformly distributed on it, and this is your central mass, of course, and this is my position vector R, and here I have my other mass M2. Well, as you can imagine, you can look at infinitesimal point masses dm on M1 and find call these R prime and write the same expression that we have there. So for example, the force that is acting on dm due to the attraction of M2, it doesn't matter which one I write because it's, you know, equal and opposite. In this case, it will be G dm M1 over, so we can call this infinitesimal force if you like, over R cubed prime R prime vector, okay? And so the total force now, F M1 M2, will be basically the integral of that df, right? dm M2 over the entire object that I called M1. And given the symmetry that you have for a sphere and the fact that the mass is uniformly distributed, you can easily see how the resultant force basically, you know, if you look at this expression, you're basically only integrating, well, M1 can go out, you're integrating what? You have G, M1, and then you have the integral of dm R prime over R prime cubed. And you know, this will definitely result, you can show that it will result into, well, since I'm integrating on the mass actually, it will give you, well, M2 over R cubed R without the prime. So you can go through the exercise of proving this step here, but it's definitely something that can be intuitively seen given that there is symmetry there, okay? In other words, all these, if you want to do it in a vector way, all these forces that are acting, you know, if you have a force here that is acting on dm, there is a force that is mirrored with respect to R on the mass that is symmetric with respect to this line. So you do this an infinite amount of times and that's what you get. So nothing special really, but it's important because we use that for planets. We use it all the time. And it is important to remember that that law is for point masses, but we are extending it to planets, okay? We just give it for granted that we can do it, but that would not be the case if we were actually looking at a planet that is not uniformly with the same density and spherical. And in fact, when we talk about perturbations, we try to take that into account by adding terms. So for planet Earth, what happens is that that M1 becomes mass of the planet. And so this highlighted portion is what we call the acceleration of gravity. G mass of the Earth divided the distance from the satellite, from the center mass of the planet to the satellite, vector R, and GME is what we call mu, and there is a mu for each planet, and this is the value for Earth. This is the value for the mass of the Earth, and as I said, the distance is center of mass to center of mass. Now, it is important to make the distinction here. The gravitational attraction is the force. It's everything. You put the mass of the satellite, M2, and you get a force. What we usually play with is only the acceleration part, okay? Mu over R cubed R. And so gravity, what we call gravity, is the acceleration component. That's really what we use in orbital mechanics all the time. Weight is the measure of gravitational attraction using a scale. It's a reaction force, is what you measure when you hop on a scale. The one thing that I cannot stand that people, you know, even professors and students and people in this field say all the time is that in space you're without gravity. There's no gravity in space. You're flying without gravity. That is not true. there is always gravity unless you're flying in deep space so far away from any celestial object that really there's no attraction whatsoever, but that's rarely the case. What you have in space is no weight, because there is no reaction to the gravitational force. You're not pushing on a scale. You're constantly falling, but so there is gravity, absolutely. Otherwise, you wouldn't be in orbit. Otherwise, they would put you into orbit, they would kick you out of, say, the ISS, and you would go in a straight line forever. There's no orbit without gravity, so it's important to know. You know, some interesting facts about this free fall thing. You know, if we want to experiment on the ground, what it feels like to be without weight, well, you know, you can go to an amusement park, of course, and that's pretty cool. But a little more elaborate than an amusement park to reproduce the conditions for, even if it's just 30 seconds or so, of weightlessness flight is, for example, you know, parabolic flights. What they do, they put you on an airplane inside the cargo bay, and the airplane follows for, as I said, 30 seconds or so. Here it says 29. A parabolic trajectory that you know, it's trying to remove your weight, your reaction force. Okay, that's one way. For astronauts, another way to remove the weight itself is neutral buoyancy systems. So you go in a tank, you go in a pool, and the floating Archimedes principle is creating the floating force that it's more or less compensating for you know, your weight. So you're kind of floating in the tank. And then in our facility, you've seen that we use spacecraft simulators. We have one. We try to reproduce weightlessness conditions by like a scale system, like a counter balancing system, where the top will be the spacecraft simulator here, and this pedestal is connected through pullays to a deck that has the same mass as the spacecraft simulator plus pedestal. So it kind of floats when you activate these pullays, which are also air bearing driven. I'll tell you that there are some videos online of experiments using this, and I can probably show them to you if I find them. But it's extremely difficult to run. So if I actually had to build it again, I don't know that I would go this route. It's a lot of moving parts. But it's a lot of fun as well. So let me see if I can find the video just to show you. Yeah, this one here. Okay. Okay, open it. Please open in the right page. Of course not. I have two screens, and of course it's on the wrong one. Okay. You see this? So best quality for some reason. Those you see turning on are the LEDs that are tracked by infrared cameras surrounding the floor. So you will see that at some point the height increases. This is the balancing deck down here. Can you hear the thrusters going on now? So yeah, see, going up, and so it's doing the so that is one way to try to reproduce the conditions of flight. Another one that is instead purely kinematics, and what I mean by that is that there are no real forces but just simulated forces here, is what, for example, uses the National Naval Research Lab, where a spacecraft, if you want to simulate rendezvous, for example, both satellites are mounted on motorized systems that just reproduce the dynamics of radial motion. So there's really no reproduction of dynamics, while something like this tries to reproduce the dynamics, because I'm actually pushing the system around with actual thrusters. I'm not simulating it with an actuator. Same is true for all these other systems here. Even the amusement park, you're definitely trying to reproduce the dynamics, if that makes sense. Okay. Now, reference frames that we will use. There are several. The most obvious one that you probably have heard often is the Earth-centered inertial, or ECI. It is the x-axis. So again, as I said at the beginning of this class, at some point we end up mixing the concept of reference frame and coordinate systems, but they are two different things. If I wanted to talk about the reference frame, then I would have to define three non-collinear points at constant distances. And the 3 points will be the center of the planet and two other stars. One is the North Star and one is the vernal equinox direction. So there are 2 points at infinity and the center of the Earth. That is the reference frame. But then we decide to also point the axis that way. So X for ECI will be pointing to the vernal equinox. Z is the rotation of the Earth, and then you cross the two. And that's your ECI, Earth-centered inertial. It's quasi-inertial because the planet's accelerating. The center of the planet that we use as the origin, as one of the 3 points for the reference frame, is actually moving on a kind of an ellipse, circle if you like, and that is definitely an acceleration right there. So cannot be an inertial one, but it's good enough because it goes around in a year, and so this additional acceleration is not something that, when we look at a satellite around the Earth, affects us to the point of being measurable or throwing away the force model that I've given you. So that force model works well to represent the motion of a satellite when the planet is perfectly spherical and a constant density, if I use ECI, and that's the one that is used all the time. By the way, this one is, I think we're still using the J2000 ECI, which means that the Earth's mean equator and equinox were frozen at 12 on the 1st of January of 2000. That's why we call the Julian date as the date J2000, and I believe it is changed then every 25 years. So let's see, yeah, I believe it's changed every 25 or 50 years. So every many decades we decide to reevaluate the direction of the equinox, and the new axis is established, and that's an accepted way of doing things that all satellite operators abide by. But you may actually use old ones. For example, M50 was basically similar to the one that we're using now, the J2000. It was defined in the 1950 year, 1st of January. Then you have the geocentric celestial reference frame is Earth-centered, and no need to redefine it too much. We're not going to use it. True of date, mean of date, etc. There's a lot of other reference systems that people use, but really the most commonly one is the ECI J2000. And so the first comment on this slide, given the precession and notation of the equinox, the ECI is defined at a certain time, and then as I said, it's not fixed forever. It is changed very slowly over decades, but we do update it. So it's just for you to know that you can find all these definitions when you use. How many of you have used SDK, Systems Toolkit? We use it on a regular basis. We're not going to use it in this class, but these are type of reference systems that you may see in SDK. Okay, another important one that we'll definitely use for the second homework is the one that goes with the satellite, or called the local vertical, local horizontal, or also you can see it defined as RSW, R as radial, S as, honestly, I don't know why is S in the direction of speed, I guess, velocity, but it's not always the case unless your orbit is circular, and W has to do with, you know, normal, the angular momentum direction. So there are different ways that you find in literature for the definition of LVLH. It's just naming the axis differently. Now, the one that you see depicted here is the one borrowed by from the aircraft world, where for an aircraft you would call the yaw axis the one that points down at the planet, at the Earth. The direction of flight X is the roll, and pitch is, you know, the direction that tells you if you're, you know, pointing down or up with the aircraft nose. And so that's one that you could use. But the one that I use, for example, in my research, when I talk especially about spacecraft relative motion, and I centered this LVLH on at the center of mass of a spacecraft, is actually the following. I use X pointing from the planet to the satellite, so away from the planet. The Z-axis is actually the one that is normal to the orbit, and Y completes the basis. Because Y, so which is here the X, it doesn't have to be necessarily parallel to the velocity. In fact, as you can imagine, on an ellipse like this, just point in any location that is not the perigee or apogee, you will definitely have that X is not pointing like the velocity. So that's a given. But LVLH is important because, you know, it is attached to your spacecraft, and it's giving you important pieces of information, like where is the planet down there, and which way you're going, the velocity direction, and what is the normal to the orbital plane. So this is used on a regular basis. More references that we'll definitely use is, well, the body fixed. That will be centered in the spacecraft, center of mass, definitely not inertial. Same for FDLH, is definitely not inertial. And I'm assuming that everybody is, you know, good enough with the concept of inertial reference frame. I have alluded to yesterday when I said F equal ma. The definition of an inertial reference frame is really one of those things that it's not that rigorous if you think about it, because you could say that an inertial reference frame is one where F equal ma works, and that's a perfectly fine definition. You can say that an inertial reference frame is the one that looks at three distant fixed stars, but, you know, there's nothing really fixed. The stars will change eventually position over a very long time. But so basically the concept of this absolute non-accelerating reference frame, it's an artifact. It's something that actually we're not able to define rigorously, but as long as F equal ma works well enough for our experiments, for our observations, we have a reference frame that we can call inertial. That's something that I always underline, and it's important to know. Anyways, the body fixed one is definitely not an inertial one, and usually is the principal axis of your spacecraft. It's absolutely important to define it, because otherwise you're not controlling anything in terms of attitude. You could see, you could need to use, for example, the one that actually rotates with the Earth. It's not the ECI anymore. It's Earth fixed. It's rotating, you know, every 24 hours. If I have to draw a ground track, I want to know the projection of a spacecraft on the planet, then I need to use this one. Then there are other ones that could be of interest. Spacecraft fixed inertial is not inertial because it's centered at the spacecraft center of mass, which is on an orbit, so definitely accelerating, but the axes are parallel to ECI. And it is used for attitude, especially for astronomical missions such as the Hubble Space Telescope. So imagine you center yourself at the center of mass of the spacecraft, but the axes of this reference are just pointing to the vernal equinox, North Star, and cross product of the two. So they're pointing at infinity at all times. And then, you know, if you're going on interplanetary travel, then you move everything to the sun. So instead of the ECI, you have the equivalent of ECI just centered at the sun. Not something that we'll probably use. Okay, so the two-body problem, what we really care about, was solved by Newton using the 3 laws of motion, the gravitational force, and integral calculus. You assume that the planets are the spheres, that the mass is uniformly distributed, and they are, the planet and the orbiting mass, our satellite, are isolated systems. So forget about the moon, forget about the sun, forget about everything else. You only have your ME, the planet, and your little m, the satellite. And so we call G, ME, mu, as we said, and without proof, but it's something that you can definitely find in astrodynamics textbooks. You will find the following, that the vector R connecting the central mass of the Earth and the planet obeys, basically the trajectories are conical trajectories. We'll see in the next slide what that means, conics, which is section of cones. And in polar coordinates, this is the law according to which the magnitude of the distance between central mass and central mass changes. So you define a line, and that's usually the line that connects the center of the planet and the closest point between ME and M, or perigee. And so you start counting angles from there. And if you do so in polar coordinates, this is the orbit equation, if you like. R is a function of this quantity P, which is angular momentum of the orbit squared over 2, over 1 plus E, eccentricity of the orbit, cosine of theta. Okay. Now, I'm assuming that we all know how to compute H, how to compute the eccentricity, but we can definitely refresh those later on, maybe after a break. I think I'm doing that actually in my code initializing the final assignment, the homework too. So these are basically orbital parameters kind of discussion that we have to do. But basically, let's go from this, that the position of the magnitude of the position vector is changing only with theta, because E will be a constant and H will be a constant of the motion for this particular hypothesis that we made, the simplified Keplerian orbit. Now, the two-body problem is based on conics. As I say, it results into conics. And so what that means is that the trajectories of your satellite around the planet will be either circles, ellipses. You're cutting this symmetric two-cone system with a plane. And if you put the plane normal to the symmetry axis, you get a circle. If you incline it a little bit, you get an ellipse. If you keep inclining it, you cut it in two different portions and you get an hyperbola. If you get it parallel to one of the sides, you get a parabolic trajectory. In the equation that I showed you before, as I said, R is the radius vector's magnitude. Theta is called the true anomaly and is called measured from the periapsis, which is the closest point between the objects in the orbit. P is called the semilatum's rectum. H is the angular momentum of the orbit, and E is the eccentricity. And we know that eccentricity is 0 for a circle, between 0 and 1 for an ellipse, equals to 1 is a parabolic path, and 1 is an hyperbolic path. So I definitely don't want to go too far into astrodynamics, because that's not the goal of this class. But it's good to remember that also the mechanical energy for closed orbits, circular and elliptical, is defined as the potential plus kinetic. So per unit mass. So it's a v squared over 2. And then there is a term that is minus mu over r, which is the potential energy of the attraction from the planet. And so for a closed orbit, it's always negative. So in other words, you don't have enough kinetic energy to escape. You remain stuck into a closed motion you keep folding around the planet, you're kind of in a sink and you stay there. If you have just enough velocity to escape, then you end up in a parabolic flight, which is a zero mechanical energy. In other words, your kinetic energy and mechanical energy, and potential energy, gravitational energy are the same. And so you have just enough velocity to never come back, but you end up, we say, at infinity with zero residual velocity. So from a sun's perspective, what would happen is that you end up moving around the sun with the same velocity as the Earth. You go into orbit around the sun like the Earth, pretty much. You just never come back to Earth, but you can't really go beyond escaping Earth. You can't go to another planet. If you actually want to go to another planet, then you will have to go on a hyperbolic flight, where the mechanical energy now is positive, so your kinetic energy exceeds the potential one of gravitational attraction, and now you can actually go to infinity, or basically leave planet Earth, leave the sphere of influence of the Earth with the residual velocity, which is non-zero. But this is topic for another class. We'll definitely deal with elliptical closed orbits that will simulate for this class, and this is a nice image that shows you, key parameters. So your planet will be the one of the focal points, occupies one of the focal points of the ellipse. Well, here ni will be theta, is the true anomaly. Periapsis or perigee for Earth, apoapsis or apogee for Earth are the closest and furthest away points of the satellite, from the satellite to the attracting body. The same major axis can be measured. It's this length. The ellipse is of course symmetric, so you have the two symmetry axes, and so the semi-major axis is half of the longest symmetry axis, and the semi-minor, of course, is the half of the shortest one. And then eccentricity, well, you can't really visualize eccentricity, but it's a measure of how elliptic you are. It collapses to zero if A and B are the same, which is a circle. So you collapse to having just a radius because it's a circle, and it grows as you make the ratio between A and B bigger and bigger. And there are other properties such as same major axis times eccentricity will measure the distance from the center of the ellipse to the focal point, and so on and so forth. The periapsis is measured by A times 1 minus E. The apoapsis is measured as A1 plus E. The orbital period, which is one of the Kepler's laws, is given by this expression. See, the square of the orbital period is proportional to the cube of the same major axis. So if you solve for t, this is what you get: 2 pi square root of same major axis cubed over mu. So the bigger the orbit, of course, the longer it takes to go around. ISS takes about 90 minutes. It's at about 400 kilometers above the Earth. A geostationary satellite is 36,000 kilometers above the Earth and takes 24 hours to go around. For a circular orbit, nothing special. It's really not that exciting. The velocity is always normal to the position vector. We have some examples of circular orbits here with the periods. I was alluding to them. A low Earth orbit at 300 kilometers takes about 90 minutes. At 400, just a little bit more. Medium Earth orbit, say 3,000 kilometers, is 150 hours. GPS is 20,000 kilometers. These are altitudes, by the way, so you're not including the 6,378 average Earth's radius, but you could add it if you wanted distance from the center. And it's a period of 720 hours, and then geo is 24 hours. Well, this is in minutes, I'm sorry. Yeah, 720 minutes, and so these are about 24 hours. And these are the velocities. Of course, the closer you are, the faster you need to go, because you have one way to see it is you're constantly falling. If you are on an orbit, you are a stone thrown at enough velocity that you keep falling, but you never touch the ground, right? And so if you're closer, the attraction from the planet is stronger. You better fly faster so that you keep falling without actually going on the surface of the planet. And so you're talking about more than 7 kilometers a second in LEO, and it goes to less than half when you are in GEO. So these are just, important values to know. Now, let's see an orbit in 3D, which is a lot more interesting than just putting it on a plane. And this gives me a good excuse to introduce the orbital parameters. How do we represent the position of a satellite in orbit? Of course, you can do it with the radius vector. Let me go back a few slides. Remember, this is the what is it? This is one way to do it. You have the magnitude of r, but you also have the vector r. You can numerically integrate an equation like, sorry, I'm going back a lot of slides here. Basically like this one. Just remove the mass, divide by the mass, you would have r double dot here, which would be the acceleration of your satellite, which is equal to mu over r cubed r. You integrate that numerically, like you're doing for your homework one, and you have Cartesian coordinates in ECI for the position of your satellite. So in this x, y, and z axis, you will have at all times through numerical integration, you will have x, y, z, x dot, y dot, z dot of your satellite, and that's perfectly fine. And in many cases, it's what we need. But much more convenient and visual are the orbital parameters. Now, it's been an hour almost. I suggest that before I move on with orbital parameters and what's coming next, we take a short break, if that's okay with you guys, because I need a break. Need a cup of coffee.
Okay.
Yes.
Okay. Any questions before we take the break, though? All right. So I'll stop the recording and I'll see you here at, what time is it for you there? 4? No.
5.
Sorry?
5 p.m.
It's about 5, so 5:05 or so?
Okay.
5:10? Let's take 10 minutes. 5:10.
Okay.
Yeah.
Okay.
Okay.